There's a phrase that I think pretty much every single one of us has used at some point.
Oh, absolutely.
Usually it's when you were a teenager rolling your eyes at your parents, or maybe it's just like, 5 p.m. on a Friday and you are completely burned out.
Yeah, I know exactly the feeling you're talking about.
That phrase is, I don't care.
It is a classic. It's the universal signal for apathy. Usually implies laziness or checking out or just, giving up on whatever the problem is.
Exactly. It sounds like you're quitting. And this is really why I love digging into these technical stacks we get for the show in the world of computer engineering and digital logic. Saying, I don't care isn't lazy at all.
Not even a little bit.
It's actually a superpower. It is a strategic weapon.
It really is. It's a fundamental pillar of efficiency. Because, well, if computers cared about every single theoretical possibility, they would be incredibly slow, they'd be massive, and they'd probably overheat in about 10 seconds.
So today, we are doing a deep dive into don't care terms. And no, for you listening, that isn't a list of people who ghosted me. Let's hope not.
It is a very specific engineering concept that basically allows our devices to function at the speeds we expect. But, and here's the twist we are going to get to a bit later, if you aren't careful with the things you don't care about, they can actually come back to haunt you in some pretty catastrophic ways.
That's the core tension of this entire field. It's about knowing what matters and strategically ignoring what doesn't so you can build a better system. But if you ignore the wrong thing, well, you end up in what the documentation literally calls a walled garden of error states.
Which, sounds lovely, but is actually a total nightmare.
A complete nightmare, yes.
So we have a great stack of source material today. We've got technical documentation, some encyclopedic records on digital logic design, and a bunch of files specifically focusing on Boolean functions and circuit minimization.
It's a really comprehensive pile of sources.
It is, and our mission today is to figure out how engineers decide what to ignore to make things faster, cheaper, and smaller, and what happens when it all goes wrong.
Sounds like a plan. Let's start right at the beginning with the definition. When a logic designer says don't care, what are they actually looking at on their screen?
So in the strictest definition from the encyclopedic records, we are looking at a Boolean function.
Right.
Basically the math of logic, the zeros and the ones.
Right.
A don't care term, which is often abbreviated just as DC, is an input sequence, a specific series of bits for a Boolean function where the output effectively does not matter.
Okay, let's make that concrete for the listener. The system receives a message, like a specific pattern of bits, and the designer basically says, if you hear this specific sequence, I really don't care what you do.
Precisely. But they don't say that out of laziness.
Yeah.
It's usually because that specific input sequence is totally irrelevant to the function at hand.
Right.
The history of this is actually great because the names for this concept in the older literature are incredibly descriptive. You will see them called redundancies or irrelevancies.
I actually found a few more colorful ones in the notes that I really liked. Vacuous combinations.
Which sounds a bit harsh, honestly.
Yeah.
Like an insult you would hear in a Victorian novel.
Vacuous combinations.
Exactly.
Or they call them forbidden combinations. And my personal favorite, logical remainders. It sounds like a progressive rock band.
It really does. But forbidden is actually the best hint at what's going on here. The reason the designer doesn't care about the output for these terms is that they have the freedom to choose it arbitrarily.
Now explain that freedom, because usually in engineering, precision is everything, right? You don't just get to choose your output on a whim. If I press A on my keyboard, I want an A to pop up, not a Q, just because the engineer felt like it.
Well, think of it this way. If I tell the circuit, I don't care if the output is a 1 or a 0 for this specific input, that gives the mathematical model flexibility.
Okay.
I can assign it a 1 or I can assign it a 0, and I get to choose whichever one makes the overall math equation simpler.
Oh, I see. So it isn't just ignoring it, it's using it as a tool. It acts like a wild card.
Exactly. It is a wild card. By picking the most convenient output for those don't care spots, we achieve minimization.
Minimization.
Right. We can make the circuit simplest, smallest, fastest. We can make it cheapest to manufacture, or we can use it to reduce power consumption.
So if assigning a 1 to that don't care spot allows me to group a bunch of other signals together and maybe, I don't know, delete a physical transistor or remove a wire entirely, I just do it.
You do it immediately. In the old days, this saved actual physical bulky components. Today, inside a microscopic silicon chip, it saves space and energy. Every single logic gate you remove means less heat generated by the processor.
Okay, let's unpack this minimization concept a bit more, because I think when people hear minimization, they might think cutting corners. Like, oh, we didn't bolt the bolts on the bridge to save money. But you're saying it's really about pure optimization.
Right. It's elegance, not laziness. And to truly understand that, we have to look at the logic of ignoring things. There is a subtle but absolutely critical distinction in the source material between a pure don't care term and what is called a can't happen term.
A can't happen term. That sounds pretty definitive.
It is definitive.
Yeah.
A can't happen term is an input sequence that we know, either physically or logically, will simply never occur in the normal operation of the system.
Give me a real-world analogy for that, because input sequence can feel a little abstract if you aren't staring at code all day.
Okay, think about a standard digital calendar.
Okay.
You have inputs for the month and inputs for the day.
Right.
If the input for the month is February and the input for the day is the 30th, that is a can't happen term.
Oh, because February 30th doesn't exist.
Exactly. So if you are designing the logic for what that calendar application should do, you do not need to write a specific complex rule for February 30th. You don't need to say, if Feb 30, then display a giant error message. You just don't care.
Because the user physically can't select it from the drop-down anyway?
Ideally, yes. So seeing February 30th is a can't happen event.
Okay, so if I'm the designer and I have this wildcard freedom, do I just let the system crash if it somehow happens? Or do I actively use it?
Well, here is the key takeaway from the encyclopedias. To a logic designer, a can't happen term and a don't care term are treated the exact same way.
They are.
Yes, they are both just opportunities for optimization. If you know an input can't happen, you don't care what the output would be if it did happen.
Because theoretically, it is never, ever going to happen.
In theory. And that's exactly where the optimization comes in. Engineers use specific tools to visualize all this. The sources mention methods like Karnaugh maps.
K-maps. I saw these in the documentation. They look like little grids of squares. It honestly looks like a Sudoku puzzle.
It's a bit like Sudoku, or maybe Tetris. You map out your ones and zeros on this grid. Each square represents a combination of inputs. And then you have these blank spots on the board. Those are the don't cares.
And the goal is to circle groups of them, right?
Yes. The goal of the K-map is to draw boxes around groups of ones to simplify the logic. And the mathematical rule is the bigger the box you can draw, the simpler the resulting circuit becomes.
So if I have a don't care square sitting right next to a bunch of one squares.
You should pretend that don't care is a one. Now your box is bigger. Your logic is simpler. You have just saved a logic gate.
That is incredibly satisfying. It's like connecting the dots, but you get to draw extra dots wherever you want just to make the picture look better.
That is a perfect way to describe it. There is also the Quine-McCluskey algorithm, which is heavily featured in the notes. That's essentially just an algebraic way to do the exact same thing for much more complex systems where a grid is just way too hard to draw by hand.
I do want to touch on a bit of the historical context here because the notes mention a guy named Seymour Ginsburg back in 1958. This seemed like a massive turning point in how we actually understand this efficiency.
Yes, Ginsburg. This part is fascinating because it really highlights the physical limits of early computing. In 1958, they simply didn't have the processing power we have now to design chips. They were working with much clearer constraints.
Right, because today we just assume computers can optimize anything instantly. You type code, and the compiler fixes your mess behind the scenes.
Back then, Ginsburg proved something that was actually quite counterintuitive. He was looking at finite state machines. Those are basically systems that move step by step from state A to state B.
Okay.
He showed that just because you minimize the states, like reducing the number of actual steps it takes to do a job, it doesn't necessarily mean you have minimized the logic elements.
Wait, that sounds completely backwards. If I have fewer steps, shouldn't I automatically have less hardware? If I build a machine with 3 gears instead of 4, it should be a smaller machine.
In mechanics, yes, but in logic, not always. Sometimes, describing a shortcut takes a much more complex vocabulary than just taking the long way around.
Oh, I get it.
Imagine trying to explain a shortcut through a city that involves 6 very specific left turns through back alleys versus just saying, stay on the highway. The highway is technically longer, so it has more states, but the instruction is much simpler, less logic.
That makes perfect sense. So Ginsburg proved mathematically that simple behavior doesn't always equal simple wiring.
Exactly. And he pointed out a major historical limitation. Calculating the absolute perfect direct minimization using these don't care conditions for large systems was computationally impractical in 1958. They fully understood the theory, but they couldn't always brute force the perfect solution.
So they basically had to make trade-offs. They knew they were leaving some efficiency on the table because they just didn't have the computers to calculate how to build better computers.
Which is humbling, honestly. It shows that even the concept of strategically ignoring things requires a massive amount of calculation to get right.
Let's try to really ground this for the listener. We've been talking a lot about logic and sequences and algorithms. Can we give a concrete example of where a don't care term actually lives inside a gadget that I might recognize?
The absolute classic example, and the one the source material highlights heavily, is BCD, binary coded decimal.
Binary coded decimal. Break that down for us.
So ideally, computers just like binary, pure ones and zeros. But humans, we like decimal. We like our digits 0 through 9. BCD is a specific way of encoding those human-friendly digits using exactly 4 bits of binary code.
Okay, 4 bits, so that's 000000001 all the way up to weight. 4 bits. That's 2 to the power of 4. That is 16 combinations.
You got it. 4 bits can count from 0 up to 15. That's 16 possible combinations. But for BCD, which represents just a single decimal digit, we only actually need 0 through 9.
So what happens to the binary codes for 10, 11, 12, 13, 14, and 15?
They are the don't care terms. The sources refer to them as pseudo-tetrades.
Pseudo-tetrades. That sounds like a dinosaur. Or maybe a very specific weird geometric shape. Look out, a wild pseudo-tetrade appeared.
It does sound ancient, but it simply means they are combinations of 4 bits that in the specific language of BCD are complete nonsense. They are totally unused.
So if I'm building a circuit for, say, an old school alarm clock with those glowing red 7-segment displays.
Perfect example. Everyone knows those clocks. The displays have 7 little LED light bars arranged in a figure-8 pattern. To make the number 1, you light up 2 bars on the right. To make the number 8, you light up all 7 bars.
Right.
Now imagine you are the engineer designing the circuit that controls just the lower left vertical bar of that display, just that one little line.
Okay.
You need to tell that bar exactly when to turn on. It turns on for the number 0, the number 2, the number 6, the number 8.
And it stays off for 1, 3, 4, 5, 7, and 9.
Correct. But what about inputs 10 through 15?
Well, the clock is only ever supposed to show 0 to 9. If my bedside clock shows a 12 in a single-digit spot, something is very physically wrong with my bedroom. So the chip should never, ever receive a 12.
Exactly. It's a can't happen term. So for the inputs 10 through 15, which is binary, 1010 through 11111, the designer just says, I don't care. If the chip did somehow receive a 12, it literally does not matter if that lower left bar lights up or not, because the user is never supposed to be in a situation to see it.
And by saying, I don't care, the math for that lower left bar gets easier.
So much easier. The Boolean function can be simplified significantly. Without the don't cares, the logic equation might be huge because you have to explicitly tell it to be O off F for 10, O off for 11, O off for 12. But if we treat those unused numbers as wildcards, we can simplify the equation down to practically nothing. You save actual transistors on the chip.
That is really cool. It's kind of like cleaning your room by shoving everything into the closet, but because nobody is ever allowed to open the closet, the room is technically clean.
In a way, yes. You're optimizing the visible space by utilizing the forbidden space. And there is actually another super quirky example of this in vintage hardware, write-only registers.
I saw this in the notes and it confused me. A register is basically a memory slot. So this is a slot that you can write data to, but you literally cannot read data from. That sounds useless. How do you know what's in it?
You don't. It is strictly one-way communication. In older hardware, reading data back out required extra logic gates. It needed extra wires, extra multiplexers. If the designer desperately needed to save space or cost, and the software didn't strictly need to check what it just wrote, they would just completely leave out the read circuitry.
So what happens if a programmer makes a mistake and tries to read it anyway? Like, hey, computer, what number's in that box?
You get a don't care result. You just get garbage data.
So the computer basically just shrugs and hands you whatever random electricity happened to be nearby.
Basically, yeah. It might return all zeros, all ones, or just pure static noise. It is a direct consequence of don't care optimizations. The engineers actively traded functionality, the ability to read for hardware size. The output for read was explicitly defined as a don't care.
Okay, so we've got a good handle on the hardware side, but I want to transition to the software side, or at least the simulation side of things, because the technical docs mention this somewhat mysterious X value.
Ah, yes, the X factor. This is where things get really interesting and honestly where the critical distinction between simulation and physical reality becomes so important.
So in hardware description languages, things like Verilog or VHDL, which engineers use to code the hardware before it's actually built in a factory, you have 0, you have 1, and you have X.
Right. In multi-valued logic for Verilog, it's literally just X. In VHDL, it can be X for a forced unknown or sometimes a W for a weak unknown.
A weak unknown. That sounds like me trying to remember where I parked at the grocery store. But what does X actually mean when you're running a simulation on a screen?
In a computer simulation of a chip, an X usually represents a problem or a transition state. It might mean you have a flip-flop, a little memory storage unit that simply hasn't settled yet. It's in flux.
Okay.
Or, and this is worse, it could mean you have two different sources trying to drive the exact same signal at the same time. One wire is trying to say 0, and the other wire is trying to say 1.
So it's a conflict.
A massive conflict. The simulator basically throws up its hands and says, X, I don't know who wins. It's a very useful way for the simulation to tell the engineer, hey, your logic is ambiguous right here.
And I think here is where it gets really interesting for anyone trying to wrap their head around this. You can't have an X in real life, can you? If I took a physical voltmeter to a physical wire inside my laptop motherboard, the dial wouldn't say X.
No, you cannot measure an X. And this is a concept that actually trips up a lot of students and even junior engineers. An X value simply does not exist in synthesized hardware, in reality.
Because physics is physics. There is either a voltage on the wire or there isn't. It's not magic. It's not Schrodinger's cat.
Exactly. The voltage is always either a 0 or a 1, assuming it's within the logic thresholds. The real problem is, because of that conflict or that unsettled state we saw in the simulation, we as the observers don't actually know which one it is.
It's just a ghost in the machine.
It truly is. The specific 0 or 1 is not determinable from the inputs. So in the real physical world, the chip isn't outputting a magical X state. It is outputting a 1 or a 0, but it might be flickering rapidly or it might be stuck, and we just can't predict it based on the logic rules we wrote.
That feels a little unsettling, to be honest. We build these machines to be these precise, perfectly logical beasts, but deep down there are these pockets of we just don't know.
And that leads us directly to the truly dangerous part of don't care terms. Because sometimes what we think implies I don't care actually turns into I really should have cared.
Right. Let's get into the danger zone. So we established earlier that can't happen terms are treated as don't cares. We optimize the chip, assuming they will never ever occur. But what if a can't happen condition actually does happen?
This is the absolute nightmare scenario for reliability engineers. And this is especially risky in circuits that involve feedback, things like state machines, where the next step the machine takes depends entirely on the previous step it just took.
Okay, so let's visualize this for the listener. Normally, the machine bounces happily between state A, state B, and state C. It is never supposed to go to state D. So the engineers optimized state D completely out of existence. They treated it as a don't care.
Correct. We didn't build a logic path out of state D because we confidently assumed we would never get into state D.
But how does the physical machine get to state D if it's supposed to be mathematically impossible?
The source material lists a few major culprits. Power up is a really big one. When you first turn a device on, for just a split second, all the voltage levels across the board are stabilizing. The flip-flops might wake up in a completely random state.
So you turn on your smart toaster, and for one tiny millisecond, it wakes up and thinks it is in a state that doesn't logically exist.
Exactly. It wakes up in that forbidden state D. Another cause could be that the power supply fluctuated. And the other causes are even more exotic. Things like electrical noise, extreme heat, or even cosmic radiation.
Cosmic radiation. I love that actual space particles can fly through the atmosphere, flip a single bit in my computer, and cause a don't care error. It sounds like pure science fiction.
It absolutely happens. In the industry, it's called a soft error. A high-energy particle hits a microscopic transistor and literally flips a 0 to a 1. And here's the dire consequence. If that physical flip pushes the machine into a state it was never supposed to be in a forbidden input, it might get entirely stuck.
This source text uses a very poetic phrase for this specific lockup. It calls it a walled garden of states.
It is a beautiful image, isn't it? But a terrible, terrible situation for a circuit. Imagine the machine accidentally lands in one of those can't happen states. Because we treated it as a don't care to save space, we didn't program a way out. We didn't give it an instruction that says, if you find yourself here, go back to start.
We just left the logic completely undefined.
Yes. So the machine might look at its internal logic table, see that the next step from this impossible state is just another impossible state, and it just bounces around in this walled garden of invalid states, unable to ever get back to normal operation.
That's a hardware lockup.
That is your computer freezing completely and needing you to pull the plug for a hard reboot. It is literally lost in a logic maze that has no physical exit.
That is terrifying for anything mission critical. I mean, if my smart toaster freezes in a walled garden, fine, I get burnt toast. But what if it's a pacemaker, or a communications satellite, or the anti-lock breaks on a car?
Exactly. That is where the stakes completely change. So responsible designers have to ensure that can't-happen states are truly impossible. Or, if the safety is critical, they simply cannot use those states for optimization. They have to leave the efficiency on the table.
So you have to sacrifice the smaller chip size. You have to leave the extra logic gate on the board just in case.
You have to. You design what the document's called don't care alarms.
An alarm, like a physical siren, goes off.
Essentially, it's logic that detects if the machine enters a forbidden state. It flags an emergency signal to the main processor. Or, even more commonly, you design the logic so that all those unused states automatically transition back to a known, safe, normal state. These are called transitory states.
Oh, like self-healing logic.
Yes. It assumes the impossible might actually happen due to a cosmic ray or a power surge, and it deliberately provides a path home. It explicitly says, if you wake up in state D, go immediately to state A. It costs more logic, it makes the physical chip slightly bigger and more power-hungry, but it prevents the walled garden scenario entirely.
So it really just comes down to how much do you trust the universe not to mess with your voltages today?
Pretty much. If you are building a cheap plastic toy that sings when you press a button, you optimize everything, use all the don't cares, and you risk the lockup. If you are building the navigation system for an airplane, you build the path home.
This has been a really enlightening look at something that sounds so dismissive on the surface, don't care, but really, it is entirely about efficiency.
It is. It's about recognizing that not every single input requires a specific, thoughtful response. Strategically ignoring the impossible allows the possible to run smoother, faster, and cheaper.
It's focusing purely on what matters.
Exactly.
But as we learned with the walled gardens, you have to be careful, because if you ignore the wrong thing, or if the universe decides to force an impossible input on you anyway, you end up trapped.
It is the absolute classic engineering tension. Optimization versus robustness. You can strip everything down to the bare metal to make it blazing fast, but you lose that critical buffer against the unexpected.
Before we go, I want to leave you, the listener, with a thought about that X value we discussed. You mentioned that in reality, X doesn't exist. It is always a 0 or a 1. We just don't know which one it is.
Right. The physics demands a value. The universe doesn't do undefined.
I feel like there's a real-life philosophy buried in there. In the simulation of our lives, our plans, our daily worries, we have all these unknowns. These X values where we feel like we are in conflict or totally unsettled. We don't know the outcome, but in the physical reality of the moment, everything already has a value. We are where we are. The outcome is already unfolding. We just might not have the inputs to determine what it is yet.
That is surprisingly deep for a technical discussion about logic gates. But it's true. The value is always there, even if the simulator in our heads can't quite see it yet.
Just don't let a cosmic ray knock you into a walled garden today. Thanks for joining us for this deep dive.
Stay curious.
We will see you sometime.